The center of a group is a subgroup that consists of all the elements that commute with everything in the group. Because it consists of these commuting elements, it's not difficult at all to show that the center of a group is actually a normal subgroup of that group. So what happens if we were to take the quotient of a group by its center? If we blind ourselves to the differences between elements of G that can be explained by commuting elements, what structures can we get? A partial answer comes in the form of what I call the Nifty center theorem. And the Nifty center theorem says, if G is an abelian group, in other words, if everything commutes with everything, then G modulo ZG, so the factor group of G by its center, is a cyclic group. That forward implication is actually really obvious, because if G is abelian, that means the center of the group is everything, because everything commutes with everything. And so if G is the same thing as ZG, then of course the quotient is cyclic because the quotient ends up being a trivial group. So if G is abelian, the quotient of G by its center ends up being trivial, which is of course cyclic. So what's interesting about this theorem is that it also goes the other way, to say that if for any group its quotient by its center is cyclic, then that group must have been abelian. And so again, sort of thinking about what this means for abelian groups, G is equal to ZG, that the only way, this is saying, that the quotient of G by its center can be a cyclic group is if that quotient ends up being trivial, because that's what happens in the abelian case. So what this means is if you give me a group and a center for that group, and I take the quotient of it, either my group is abelian and so that quotient ends up being trivial, or if my group is not abelian, then its quotient by its center cannot be cyclic. So it'll be a group that is not a cyclic group. Here's an example of how you might directly use the Nifty center theorem. So suppose for a minute that I think about the dihedral group of the square. The center of the dihedral group of the square is these two elements, the identity, which commutes with everything, but also the 180-degree rotation of a square commutes with everything. So what are we going to get if we take the quotient of this dihedral group by its center? Well, the group itself has 8 elements. The center has 2 elements, and so the index of that subgroup in D4 is 4. And so my quotient, my factor group, will be a group of 4 elements. And of course, there are 2 different groups of 4 elements up to isomorphism. One of option is a cyclic group, Z4, and the other one is the Klein 4 group, the elementary abelian group of order 4, Z2 direct product, Z2. So which one of these 2 options is it, without doing any additional computation? Well, one of these 2 groups is cyclic. Z4 is cyclic. A generator is 1, for example. And the Klein 4 group is not cyclic, right? And so we can use the Nifty center theorem here to rule out the possibility that this quotient is isomorphic to Z4, the cyclic example. Because if a group modulo its center is cyclic, then this theorem implies that that group must have been abelian. But my group, D4, is very clearly not abelian. We know just by the basic definitions of the dihedral group that D4 is not abelian. And so since D4 is not abelian, its quotient by its center cannot be cyclic, again, because this is an if and only if theorem. And therefore, since I know that the quotient of D4 by its center will be a group of 4 elements, and we have ruled out the possibility that that quotient is cyclic, we know therefore that the one non-cyclic option must be the true identity of the quotient of D4 by its center. So that's an example of an application of the Nifty center theorem to do something sort of concrete for a specific group. What I want to look at in the next video is how we can apply the Nifty center theorem to make it even more general conclusion about what we can say about whether the kernel of a homomorphism out of a group is allowed to exactly equal the center of the group. Is it ever possible that a homomorphism can kill, send to the identity, exactly all the elements of the center of G and no more and no less? We'll use this theorem in the next video to see why or why not.